the video and attempt the question on your own before moving on. Our first step to solve this question would be to draw a picture based on the given description. So here we have the rectangular storage container. We'll note that the question said that the length of the base is twice the width. So we've called this dimension the width, W, and then we've made the length twice that, or 2W. We have the height marked as well with the letter H. Our next step is to come up with an equation that is sometimes called a constraint equation. The question mentions that the volume of the storage container must be fixed at 10 meters cubed. So in other words, we are constrained to make the container have a volume of 10 meters cubed. Now, the volume of any rectangular storage container is simply equal to its length times its width times its height. Now, looking at our diagram, we have the length marked as 2W, the width marked as W, and the height marked as H, so we can fill those into our volume equation. And of course, we can multiply 2W and W to make 2W squared. Also, we can plug 10 in for the volume. Perhaps we can then divide both sides of the equation by 2. And for now, we can leave the equation in this simplified form. Our next step is to come up with a second equation known as the objective equation, and that depends on what the question is actually asking us to accomplish. If we read the last line, it says find the cost of materials for the cheapest container. Now, cheapest suggests that we are trying to minimize the cost of the container. So our objective equation should have something to do with minimizing cost. Now, to minimize cost, we have to understand what exactly we mean by cost, how we come up with it in the context of this problem. And it turns out that cost can simply be defined as the area multiplied by the price per meter squared. Now let's look at that more carefully. It mentions that the base has the cost of $10 per square meter. So let's take a look at our diagram. So we have color-coded the base in green and then the four sides of the container in blue. Remember that the container is open on the top, so there's actually no material up here. If we were to try to come up with an expression for the cost of the base, we would follow this equation here. We would take the area of the base and multiply by its price per square meter. We can see that the area is simply equal to 2W times W, and the price per square meter of the base was stated as $10 per square meter, so we can multiply that by 10. We can simplify that, of course, to make 20W squared, and that's going to represent the cost of the base of the container. Now, of course, we need an expression for the cost of the four sides. We can call the four sides right, left, front, and back. Now, hopefully we can see from the diagram that the area for the right side and left side would simply be W times H. So for those areas, we would have WH. The cost of the sides is $6 per square meter, so we would have to multiply that area times 6. Now for the front and back, we have a slightly different area. If we look at the front side right here, we can see that the area would be 2W multiplied by H. So that would represent the area of the front side. The back side, we can see, has the same area, also 2WH. And then we multiply by 6, because again, that's the price per square meter of the sides. We can simplify these. This becomes 6WH, as does this. And then the latter two become 12WH. So to get the total cost, we simply have to add up the front sides to the base. And when we do that, we can see we get a total cost equal to 36WH plus 20W squared. Now, the only problem with this equation is that it is in terms of two variables, both W and H. Well, that's where the constraint equation will come in. What we can do is solve the constraint for one of the variables, probably easier to solve for H, and then plug that in to our objective equation. So we can solve this for H by dividing both sides by W squared. And so we now have an expression for H that we can plug in to our objective equation. We can simplify this equation by canceling a W in the numerator and the denominator, and by multiplying 36 by 5. And then one last simplification before we move on. We can move the W up to the numerator. We'll see why that's important in just a moment. Remember that the exponent of 1 will become a negative 1 when we move it to the numerator. Okay, so finally we have a cost function in terms of a single variable and simplified in a usable form. Our next step, of course, is to calculate the derivative of this equation. The derivative of cost will become c prime. We can use a power rule to calculate the derivatives here. So we pull the negative 1 down and multiply by the coefficient. We get negative 180 w, subtract 1 to give us w to the negative 2. Then we can pull the 2 down, multiply it by the coefficient of 20 to give us 40 w to the first power. After calculating the derivative, we could set it equal to 0. Perhaps to solve for w, we could add 180 w to the negative 2 to both sides of the equation. We could multiply both sides by w to the positive 2, and what's nice about that is it's going to cancel with the w to the negative 2 on the right side. Dividing both sides by 40 will give us 9 halves on the right side, and then to cube root both sides would give us w is equal to the cube root of 9 halves. Or in decimal form, you could say the cube root of 4.5. Now, this is what we call a critical number. We have to confirm that this indeed minimizes the cost of materials. So to confirm that, we could use the second derivative test. So all that means is we have to calculate the second derivative. So c double prime would become positive 360 w to the negative 3 plus 40. And the idea is the following. No matter what value for w we plug in, the second derivative will always be positive. It will always be greater than 0. A positive second derivative shows that the cost function is concave up for all values of w. That means that our critical number was located at a minimum. So this indeed confirms that this value of w minimizes the cost. Now, it didn't ask us to find the value of w, it actually wants the cost. So our next and last challenge is to plug this value of w into our cost function. So here we have it plugged in for w into the cost function, and when you compute that on your calculator, you should get approximately $163.54. So that would be the approximate minimum cost of the storage container. As always, thanks for taking the time to watch this video. If you'd like to, please subscribe to the channel so you can stay tuned for additional videos. Also, you are welcome to send in your own question to the email address listed on the screen.